Thank you very much. So today is the last effort on inflation. I hope you have enjoyed the week, and I hope you enjoy more the weekend. So today, what I would like to do is to go a little bit away from the usual textbook analysis of cosmological perturbations. So I will address a couple of subjects which are related to each other. That has been the subject of work the last few years. And it's again related to the observations. So this is what I want to relate again some idea of inflation to observation. In particular, I'm going to talk about what is called the non-Gaussianity. So what is it? So far, we have been dealing with only linear perturbation theory. So if you have noticed, I've never talked about any interactions of the scalar field. I only took a massless scalar field which was free. The curvature perturbation, I never talk about any interaction of the zeta, the quantity that we introduced yesterday. But in fact, this assumption is also not correct. It is correct in first as a kind of approximation, and because we know that the perturbations are small, but in fact we know that is wrong because gravity itself is nonlinear. You know that when you write down the Einstein action and then you perturb around your background, you have lots of interaction of the perturbations. So gravity is in fact nonlinear. That's the reason why at the end of the day, when you have fluctuations which are very small, like at the level of 10 to minus 5, delta rho over rho 10 to minus 5, when this fluctuation re-enter the Hubble radius, as we said yesterday, gravity will act, and of course gravity is attractive, so it will make this fluctuation collapse to smaller and smaller scales. And of course, at small scales, gravity is highly nonlinear because gravity is a derivative theory. It goes like Laplacian or derivatives of your fluctuations. So of course, when you go to smaller scales, the gravity becomes more and more attractive. And that's the reason why you form halos of dark matter, you form galaxies and so on. But in terms of inflation, people have done a lot of effort to go beyond this linear perturbation theory. So let's discuss about the linear case first. So when you have think in terms of the harmonic oscillator, okay? Harmonic oscillator is you don't put any interaction, so you have a kind of harmonic oscillation with a potential v of x, which goes like m squared or omega squared divided by 2 times x squared, your space coordinate. And you don't, of course, it's a good exercise to put higher order terms like x cubed or x to the fourth, but for the time being, if you only restrict to the harmonic oscillator, you know that when you compute the wave function of the harmonic oscillator, you get a Gaussian. Okay, you get Hermite polynomials and so on, but the fundamental wave function is a Gaussian. So linear perturbation theory predicts that if I ask myself, what is the value of some curvature perturbation in any given point x? This quantity, it's a stochastic quantity, of course, because you cannot say precisely that any given point zeta has a given value, like 0.3, for instance. You can only write down the probability of this object here. Like for the harmonic oscillator, you can say, well, I have a certain probability that my object is at a point x in a given time t. And this probability is a Gaussian. Okay, so when you have linear perturbation theory, you know that the probability is going to be a Gaussian. Okay, with a given variance and a given vacuum station value. So we will go like e to the minus zeta square divided by the variance of the same quantity with some factor of 2 here. Okay. So, and what does it mean? It means that if I compute now the correlators of this quantity, either in space or in momentum space. So if I compute, for instance, let me see, let's go to momentum space. If I compute the correlator between zeta with a given momentum k1 and a given momentum k2, this object is not zero, because of course, as you know, for the harmonic oscillator, the x square is different from zero. Okay, so this object is different from zero, but all the odd correlators, like for instance zeta k1, zeta k2, zeta k3, if the theory is Gaussian, all the even correlators, sorry, all the odd correlators, like the 3-point correlators, will be zero. Like for the harmonic oscillator, when you compute, you don't have interaction, you compute the average of x cubed. Since your wave function are even, you're going to get zero. Okay? And of course, if you compute the 4-point correlator, let's say like for the harmonic oscillator, if you have x4, this is different from zero, because it's even in the powers. And the same thing, if you compute 4 zeta here, you're going to get result which is different from zero, and so on and so forth. Or the even correlators are not zero if the distribution is Gaussian, and all the odd are in fact zero. Okay. In terms of probability, what does it mean? The average of zero of zeta square, for instance, it means simply the integral of all possible configuration times zeta square times the probability of zeta. Okay, as long as you know the probability to find a given value of zeta in a given point, you can compute formally this object here. So it's exactly like the harmonic oscillator. In fact, as we have seen, the equation for zeta resembles, even though it's an expanding universe, an oscillator. All right, so the question now is, what happens when I include the interactions in my system? There are two kinds of interactions that, of course, you can look at. One are the interaction of the inflaton field itself, because we know that the inflaton has a potential in general. For instance, Matteo yesterday took a potential phi to the n, let's say phi to the fourth. Phi to the fourth as trilinear couplings when phi gets a vacuum transportation value, or even quartic couplings. There is another, of course, source of linearity, as I said before, is the gravity itself. Gravity is nonlinear, so we have to take into account. So the question now is, how do I parameterize, how do I take into account this nonlinear interaction during inflation? Well, first of all, I ask myself if this object here, so the 3-point correlator, is it really equal to zero or not? Well, I would expect by these arguments, because there are nonlinearities, that in fact it is not zero in general. But the question is how large it is. Is it a good approximation to have a Gaussian distribution, or do I expect some 3-point correlator and therefore a correction to this probability to be a non-Gaussian one? So this subject goes under the name of non-Gaussianity, in the sense that we are looking now at correlators which in the linear perturbation theory are zero, but in fact we know they are not zero. The other question, fundamental question, is suppose that it is not zero, is it measurable or not? And why is it important to know if it is not zero or not? Okay? So what I would like to do now is to show you that in fact this object is not zero as expected, but it is in the single field model of inflation that I described so far, in which you have only one inflaton field plus gravity. This object is small, okay? So small that in fact it's, I don't think it will be ever measured, or in any case extracted from the data that we have so far. It will be very hard to measure such an object. But I will give you another counterexample where this object, in fact, will be not only zero, but very large. That is a model where, which is also quite popular, which is called the Corvaton model, where the non-Gaussianity, in fact, is very large. So why this subject is so important? It's so important because if one day we will measure this 3-point correlator and we discover that it's large, then all the single field models of inflation, all of them with no exception, the one that Matteo described yesterday, X inflation, Starobinsky, whatever you want, all of them will be ruled out. Okay? So that means maybe, I don't know how many years, but really 40 years of research gone into the garbage. Okay? So that's the reason why it's important to measure this quantity and to understand theoretically what is the prediction. All right, so now what I want to do is to give you an hint on how to compute this object in one single field model of inflation. And I want to show you that in fact this number is going to be small. Small means practically not observable by the experiments. All right, so in order to compute this 3-point correlator, let me define, in fact, the 2-point correlator in a different way that I defined yesterday. Yesterday we defined the power spectrum. The power spectrum in momentum space can also be defined in a different way that I used yesterday. If you remember, I defined the power spectrum of a scalar field through the variance of the scalar field. There is another way to define the power spectrum, which is this. You take the correlator between two momenta, K1 and K2. This is going to be 2 pi cube. That's just a convention. Delta 3 of K1 plus K2, because of course you conserve the momentum because you have isotropy in your problem. And then I put the power spectrum here. Okay, so that's a definition of the power spectrum. It's an alternative definition of the power spectrum. All right, so now I want to compute this. In order to compute it, there are two ways again, or maybe more than two, but there is a hard way to do it. So what you have to do, you have to write down again your action. You write down your Einstein-Hilbert action, your action for the scalar field. You start changing your variables. You want to change variable in such a way to reconstruct this quantity zeta, which it's psi plus h delta phi over phi dot during the roll. You include cubic terms. You expand not only a quadratic, but you expand to cubic term in the action in such a way that when you have the equation, it's not linear but second order in perturbation theory, like you do for the harmonic oscillator in X cube. And then you can compute this object using a formalism, which is called the in formalism, which is technically speaking something that you do a variation of the technique that you use to compute scatterings. But of course, I don't have time to do all this. Okay, what I will do, I will present an argument to compute this object here, at least in one particular limit, which is called the squeeze limit. In which I will show you that this object turns out to be quite small, but we want to see what does it mean small in this case. Okay, so what I'm going to do is to, first of all, introduce a kind of a Taylor expansion. So if non-Gaussianity is small, so let me introduce this non-Gaussianity parameter that has been used in the literature all the time. So if you have your zeta, and you know that zeta is not Gaussian exactly, what you can do, you can Taylor expand somehow. You can say that zeta is zeta Gaussian, so I put a label G here for Gaussian. And then you say, well, the next correction will be some coefficient, which people call FNL, where NL stands for nonlinear. Okay, and then you put zeta G square, plus higher order, which I'm not interested in so far. Okay, so zeta Gaussian is the Gaussian part of the zeta, which has only even correlators. Okay, it's Gaussian. But of course, if I now compute zeta, 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 so the 3-point correlator of the full curvature perturbation, if it is nonlinear, you see, I will have pieces that has, I put in the first zeta, I select the Gaussian. In the second one, I also select the Gaussian. But in the first zeta, I can select this second piece. So it will be zeta g square times FNL. Okay? So you see, this object here now is different from 0 because zeta g is Gaussian, but here it's a 4-point correlator. It's even. So it will be not 0. So the goal of this research is to compute, for instance, for one single field models of inflation, what is this FNL? How large it is, right? And I want to show you that, in fact, I want to show a simple argument, and I want to show that this guy is proportional to the spectral index of the curvature perturbation and zeta minus 1. So if you remember, this number was extremely small, was 0.96 by the observation. So this FNL is extremely small. Notice that here in this expansion, I can select the zeta, I can collect the zeta, 1 plus FNL zeta Gaussian plus higher orders. So you see the expansion parameter is not FNL. When I will later on, I will give you an example where FNL can be even 100 or 1000 or 10 to the 4. But remember that FNL is not the expansion parameter. Expansion parameter is FNL times zeta Gaussian. Since we know that in first approximation this is 10 to minus 5, because we related yesterday delta t over t, which is 10 to minus 5 to zeta. If you remember, we proved that delta t over t on large scales is of order of 1/5 of zeta Gaussian. So we said, okay, this is 10 to minus 5, so zeta g is also of order 10 to minus 5. So you see this object here is for sure smaller than 1. So we are doing a good perturbation theory. It's not that we are failing perturbation theory if FNL is very large. Of course, if it is 1 billion, then of course we have a problem, but it's not the case. Okay, so we will be dealing with FNL at most of order of 100 or so. The current experiments tell us that FNL is smaller than 40 or something, so it's perfectly okay. All right, so that's the parameterization that I want to use, and I want to show that in fact now in single field model, the one that we described so far, FNL is proportional to this object here, so very small in any case, and the coefficient in front is over unity. It's not a million or something, okay? So let me give you a simple argument by which this is true. So what I will compute, of course I cannot compute, otherwise that will take so much time, but I cannot compute this 3-point correlator for all possible configurations of the K. So first of all, you notice that since you have isotropy, you have to conserve momentum. So you need to impose the condition K1 plus K2 plus K3 is equal, they sum up to give a zero. So basically you have a triangle, let's say, in which you have the K1, the K2, and the K3. They have to close a triangle by momentum conservation, or if you like, by isotropy, which we are assuming of your space. And then I'm taking now a squeeze limit. I want to work in this particular limit in which K1 in modulus, so let's say the modulus of K1 is much, much smaller than the modulus of K2, which of course will be, in this case, because I have to satisfy this condition, it will be of order of the modulus of K3. Okay, I want to compute the 3-point correlator in this limit, because in this limit I can compute it with a simple argument that is similar to what I used yesterday. Since K1 is much more than K2 and K3, So K1 very small means that the corresponding wavelength is very large, and the K2 and K3, they are very short, like this, the wavelengths. So what I will do, I will call this K long, and the K2 and K3, I will call it K short. Okay, just to distinguish long with, from short, distinguish the long wavelengths from the short wavelengths. Okay, this is what I will do. So from the point of view of inflation, if you remember the same plot that we drew so many times, you have the log of A, and here you have the log of h to the minus 1. Okay, so it means that I have three scales here, three wavelengths. I have the k, let's say the k2 to the minus 1, so the wavelengths, the k3, sorry, the k3 to the minus 1. Okay, but the K1 has gone out of the Hubble radius much earlier. Okay, so okay, I have to exaggerate a little bit, but like this. This is K1 to the minus 1. So it went out of the Hubble radius much earlier than the other one, the long mode. Okay. So what does it mean in practice? In practice, it means that if I have an observer, again, you see the argument is very simple and very nice. Again, related to what I was using yesterday all the time. The observer that is in a Hubble radius will detect this long mode as a kind of background. Okay, so I have a Hubble radius during inflation like this. I have my short modes, let's say lambda 2 and lambda 3, which are the corresponding. So lambda 2 goes like K2 to the minus 1, lambda 3 goes like K3 to the minus 1, but then I have a long mode, which is the K1 to the minus 1, so lambda 1, which is the K long to the minus 1, and those are the K short to the minus 1. Okay? So the observer that is inside this Hubble radius, and he cannot go out because he cannot get information outside the Hubble radius, is detecting this mode as a long mode, as a sort of background. Okay? So in the metric, I will have minus dt squared plus a squared of t. And if you remember, zeta is equal to psi plus h delta rho over rho dot. Now I go to the energy momentum, so to the gauge where delta rho is 0. So zeta, where delta rho is equal to 0, is equal to psi, the gravitational potential. And if you remember, the gravitational potential was sitting here. So I was writing down like 1 over 1 plus 2 psi. Okay, and then times dx squared. In fact, minus, if you remember the convention. Okay, but this object here is 1 minus 2 zeta, if I want to work in the gauge where delta rho is equal to 0. And also let me do the same approximation that I did before. Instead of writing 1 minus 2 zeta, I write down e to the minus 2 zeta, because it's more convenient. Okay, this is just a stupid approximation. So what is going to happen is that the observer that is living in this universe the metric will be minus et squared, a squared of t, e to the minus 2 zeta times dx squared. Okay, but this long mode, so since we are talking about the long mode, I can put here long, just to remind myself that it's a long mode compared to the Hubble radius. So I put also a zeta long here. Okay? And now what I can do, the observer can change his coordinates, his or her coordinates, and absorb the long mode into the coordinate, in the coordinate system. Okay? So what is going to happen is that this local observer will define a new coordinate system. So x goes into x e to the minus e to the minus zeta long, okay, in such a way that locally his metric will be minus dt squared plus a squared of t times some dx tilde square, let's say. The new coordinates, I call them tilde. So you see, it goes back to a local homogeneous universe. He has gotten rid of this long mode, okay? But then, of course, when I do the transformation like this, automatically the momentum k, which is kind of the inverse of the coordinate space, it will go in the opposite way. It will go into k times e to the zeta long. Okay? So this local observer, he will be living in a homogeneous universe as long as he's using new coordinates and he measures momenta which are a little bit rescaled. Not that much, but a little bit. Okay? So what is going to happen in this case? So now we want to compute the correlator between zeta k long, zeta k short, and zeta k short. Okay? We want to compute this correlator, but physically, this correlator, what does it mean? What is it? When you compute correlators, in practice, what are you doing? When I compute the two-point correlator of a stochastic quantity, it means that you take your environment and you test you take 2 points, for instance, at the given. So let's say that you have a given environment, and you want to compute the two-point correlators. So let's say you want to compute the correlator of zeta of x, zeta of y, where the distance between x and y is fixed to be a given distance r, let's say. Okay? So what does it mean? It means that in your universe, you take all possible points which have a distance r, okay? Something like this. So in fact, what you do, you take a sphere of radius small r. Okay, so the sphere, all them have the same radii. You put this sphere in all possible places. You compute, you measure the quantity, the two zetas in these 2 points, and then you take the average. This is what you do in practice. This is what an astronomer, when the astronomer will tell you the two-point correlator of galaxies is a given function, this is exactly what he does. Okay, of course, in a sophisticated way, not like I'm explaining, but in practice, this is what it is. So now the physics comes into the game, because now if you think in terms of this operation, if I now think in what does it mean in my box, okay, I have my two-point correlator measured in different points. So I have the two-point correlator of the two short modes, okay? But of course, the observer has also, in this box has also some long wavelength mode, which is the zeta long, okay? So this object here, if you think of it, will be nothing else than the two-point correlator of the two short modes, but computed in the environment where there is a long mode as well. Okay? And then when I take the sandwich between this object, the two-point correlator, but with the presence of this long mode, with the long mode itself, I will compute this in practice, these correlators here. Okay? Why? Because, of course, again, I am an observer. I do a transformation of my coordinates. I remove my long mode, so he doesn't know anything about the long mode whatsoever. He computes the two-point correlators, and he does the operation. He moves this box, these spheres, into all possible places. But then of course, this object will somehow feel the presence of the long mode, And how you test this presence, you correlate with the long mode, and if the result is not 0, then of course it's like measuring the 3-point correlator. So in other words, the 3-point correlator of a long mode with 2 short modes is equivalent to the average of the 2-point correlator of the short modes in an environment of a long mode. This is what in practice it is. You can show it more technically, more sophisticated way, but this is the intuition. All right? But we have computed this object yesterday. We know what it is, because we have computed the power spectrum of the zeta, and we know how it goes. It goes with certain amplitude times k to the power n zeta minus 1. Okay, so we know. So the zeta short is proportional, as we know, because I gave you the definition before, is proportional to the p of zeta for the momentum k short. But this goes like, if you remember, it goes like h squared divided by 2 epsilon m Planck square, and then there is also a dependence on k, which I can redefine to be k over some pivot scale to the power n zeta minus 1, if you remember. So this is a k short. All right. So now, where is the zeta long in this business? So why there is a zeta long object here is because this observer is using, in fact, k tilde coordinates, not k, right, to compute the 2-point correlator. So now, you see, this implies that I have k to the power e zeta long divided by k star, some pivot scale to the power n zeta minus 1. This is my power spectrum, my 2-point correlator of the short modes. But now, you see what I can do. I can simply Taylor expand, because this zeta long in any case is small. So if I now compute what is the average of zeta short with zeta long, I simply have to expand this object by 1 power. So what I will get that this goes like zeta short, and then when I Taylor expand, I also take the e to the zeta 1 plus. I will have n zeta minus 1, zeta long that comes from, so this piece comes from the e to the zeta long to the power n zeta minus 1 when I expand it, and then I contract it with zeta long, because I have another zeta long here, and of course I compute the correlator. So you see, this guy will go like the power spectrum of zeta of the short mode from here, the power spectrum of the long mode for k long, times n zeta minus 1. Okay? So you see now, if I want to identify the FNL, because if you remember, the FNL was coming from, let me go here. The FNL is a measure of the 3-point correlator. So if you remember, I wrote zeta equal to zeta Gaussian plus FNL zeta Gaussian square. If I compute the 3-point correlator, this will go like, always like FNL times zeta Gaussian square. So this goes like FNL. Here I have, I can contract. You see, I write down with zeta Gaussian square as zeta Gaussian twice, so I can contract this with this. I will have 2 power spectra, so I will get p zeta times p zeta. So you see, if I use this identification, the FNL from here will be proportional by some coefficient to n zeta minus 1. Okay? In fact, if you do the computation, what happens is that in this limit, with some convention, FNL is going to be n zeta minus 1 times 5/12. It depends on the convention. Some people have 5/6, but it's a number of order 1. Okay? So the conclusion of this argument is the fact that at least in this squeeze limit, in which you take a long mode compared to 2 short modes, the non-Gaussianity parameter, in the case in which you have one single field model of inflation, is always proportional to n zeta minus 1. So this number is of order of, so this 0.04. You get another 10, let's say. So it's 4 10 to minus 3. You get a 20 from here. So you get about 10 to minus 2. Okay, so that's a prediction of the at least in this configuration. It turns out that when you compute this object here, changing the configuration, suppose that you take all the momenta equal, for instance, a equilateral triangle. In this case, this number does not change. You always get something that goes like the Zroll parameter. So FNL is always of the order of the epsilon or eta during inflation. Since they are very small, you always get numbers of order of 10 to minus 2. Okay? But this squeeze limit allows you to compute exactly this FNL, and this is more or less the result. Okay? This number, again, is extremely small, meaning that if one day we will measure this FNL to be, let's say, 10 or something, if we are lucky, then, of course, as I told you before, all these models that people have constructed, because this is a generic prediction, they will be ruled out. Okay, so now you understand the importance of measuring this quantity in cosmology. Again, notice that this number turns out to be very small. So if I was stressing before that the expansion parameter is FNL times zeta Gaussian, so you see the expansion parameter in the case of single model inflation is 10 to minus 2 times 10 to minus 5 is 10 to minus 7. So it's an extremely good expansion parameter. You don't have any problem with perturbation theory. Okay. All right, so that's the information number 1 that I wanted to give you this morning. FNL for the Zroll single field model inflation is always proportional to n zeta minus 1, so therefore it's extremely small. This is an observed number, it's not a theoretical, so it's just it's a number which we observed. So that's the prediction. Okay. Is there any question about this construction? Yes, please. The 3-point correlator, yes. So you have to think in terms of, so during inflation, what you have your inflating volume, but of course the Hubble radius remains constant, right? So you have to imagine, I mean, physically what you have to take. You have to imagine free wavelengths which are inside the Hubble radius today. You contract them, you go to the moment where inflation was taking place. There, you do an hierarchy between the wavelengths. So the wavelengths I'm speaking about now, of course, they are inside today because they are measurable. Otherwise, I don't care about those which are outside the Hubble radius. But I want one of them to be the wavelengths much larger than the others. So in this volume that is basically my universe squeezed in, I do the average. Okay, that's what in practice the correlator means. And then, so my environment, I don't know what you call my volume is in fact this picture of my universe contracted. That's what it means. You have many Hubble volumes whose you have many spheres whose radius is the Hubble radius, and then you take all of them and you measure like this, and you do the average. I don't know if that is, maybe I did not understand your question, or yes, yes. Of the long mode, yes. Yes, because at the end of the day, you want to compute the correlator between two short modes and the long mode. So what I do, I take the 2-point correlator of the short modes, and I correlate this with the long mode. So I have to contract again with a zeta long. Yeah, this is the operation that in practice you can do. And in fact, now it's, I mean, this idea, people, I mean, how people construct, for instance, 3-point correlators in the squeeze limit by numerical simulations. They run the system, they let the fluctuations evolve, and then what exactly they do? They run many simulations with different long modes, and they take this average. It's exactly what they do, because it's intuitively it's the correct way of thinking. It's a very practical way and pragmatic way to compute this 3-point correlator. They don't compute the average of the average of 3 zeta in 3 different points. They run the simulations. They only measure the 2-point, but then they take the average. So it's another way to go, but it's the same result. All right, so now in the remaining time, I want to give you another example where, in fact, this FNL is extremely large, and but that will help somehow to understand that you have to depart from the usual standard picture that you find in all the textbooks. But in any case, it's a very simple picture, so something that people have been working on for many years. And we don't know where the truth is. Maybe inflation took place with one single scalar field, but maybe there was something else. So let me now talk about this something else. It's a very simple model, very simple construction, so that was pointed out some years ago, and it is as simple as the one that I described so far. So from the point of view of elegance or mathematical complexity, is not particularly disfavored compared to the single field. So what is this? You have a period of inflation. Okay, which is driven by the inflaton. Okay, but there is another scalar field, let's say a massive scalar field, which, let me call it sigma of x and t, which in the literature is called the Corbaton, and we will see why it has this name. Okay? So even we can say with no interaction whatsoever. Okay? Well, let's take the simplest scale. So I have a model where my V of sigma is simply m squared divided by 2 sigma squared. Really the simplest case you have. Now, you might think, but why I have to complicate my life like this? Well, you know, in general, when you construct a model of inflation, the model is within a given theory, and of course, the opposite, to say that there are no extra fields, is a strong assumption. I would say that it's even more probable to have many other degrees of freedom in your business, in your model, that may or may not play a role. So, and this is just the simplest possibility. You have an extra scalar field with zero mass, with a given mass. So, let's suppose also that during inflation, the mass of this scalar field the mass square is smaller than h squared. So in practice, I can consider it from the point of view of the fluctuation, I can consider it massless, okay? But we know everything about this field because we computed the fluctuations during inflation to be the fluctuation of h over 2 pi with a basically flat spectrum. We know what is the power spectrum of this field. Let me put it delta sigma is equal to simply h over 2 pi. During the third lecture, or Thursday, we talk about this scalar field. We call it chi, but let's call it sigma now, because that's the object that, the symbol that usually people adopt. Okay, we know everything about this scalar field because we do the computation. It's a simple free scalar field. It behaves like the fluctuation goes like h over 2 pi. The spectrum, the spectral index is more or less of order of -2 epsilon, and so on and so forth. So we know everything. Flat spectrum, we're done. Okay, then we say, but okay, fine. What is the role of this field? Well, the role is the following, because this field, since he is quantum mechanically excited, it will during inflation, it will not sit at its minimum because there are quantum fluctuations. So this field will do something like this. So this is V of sigma. This is the potential, simple one. So during inflation, since the typical fluctuations are of order of h over 2 pi, what happens is that this field will sit at some point, more or less. I mean, where exactly depends on the fluctuations, but in general, you won't be sitting at the minimum, okay? And then during inflation, it stays there because we were supposing that the mass is very small compared to the Hubble rate, and so it does feel the friction, so it remains basically there. And now supposing inflation ends, okay? So you have a period of inflation driven by another scalar field that you call inflaton. You don't know what it is, but you have also another light degrees of freedom that you might have in your system. During inflation, it is displaced from its minimum, and then it stays there, and then inflation ends, okay? The moment inflation ends, as you know, the Hubble rate drops. So if I write down the equation of motion of the zero mode of this guy, will be 3 sigma double dot plus 3h sigma dot plus m squared sigma 0 equal to 0, okay? So as long as during inflation h is much larger than m, the solution is sigma dot 0. So when m is much more than h during inflation, the solution is roughly sigma dot 0 equal to 0, so the field stays there. But the moment that m becomes larger than h, because of course after inflation the Hubble rate drops because the universe becomes matter dominated and h squared goes like 1 over a to the fourth, this guy will start oscillating, okay? We know it, like the inflaton field. So this guy will start oscillating around its minimum, okay? And we learned yesterday for the inflaton, but you do the same computation for this guy, that the fluctuations, the rho sigma, will start going like a to the -3. You remember yesterday we did the exercise when the field is oscillating around the minimum, when the mass is larger than the Hubble rate, the energy density drops like a non-relativistic fluid, okay? So what is the typical fluctuations in delta rho over rho of this guy? So if I compute the zeta sigma, which by definition is psi plus h delta rho sigma over rho dot sigma, okay? So that's also a gauge invariant quantity. It is equal to psi plus h delta rho sigma divided by, here I use the fact that it's the equation of motion is going to be rho sigma plus 3h rho sigma equal to 0 because it is non-relativistic fluid. So here I put a -3 h rho sigma, so the h goes away. And if I compute this object in the flat gauge, psi equals 0, I get simply -1/3 delta rho sigma divided by rho sigma, okay? So after inflation, this guy is oscillating, and its curvature perturbation associated to this is going to be this, all right? But now, let's compute this delta rho sigma over rho sigma. It's very easy because, in fact, what it is. I do perturbation theory, linear perturbation theory so far. So I don't change my assumption of linearity. So I do what is delta rho sigma over rho sigma. It's going to be m square times delta sigma, because remember that the V is m square divided by 2 sigma square, but when I have an oscillator, the kinetic term and the potential is the same, so they sum up and the factor of 2 disappears, so I have 2 here, because in fact the rho sigma is going to be m square sigma square, okay? So it's a factor of 2, but for the time being this factor 2 is not relevant, and then I have m square, so here I put the sigma, of course, sigma. Okay, sigma 0, let's say, that I expand around the expectation value square. So what I get 2 delta sigma over sigma 0. Okay? But then, what is this ratio? This ratio, if you remember, the scalar field is basically not interacting, so the equation of motion for the 0 mode is this, the one that we wrote before. But the equation of motion for the fluctuation is also this. It's the same, because the field is linear. Sorry, it's not coupled to anything. So it's going to be this. Okay? It's the same equation, in fact, because I have no potential. Well, apart from this, from the mass squared, of course. So you see, this ratio remains constant during the oscillation. It's the same ratio you had during inflation, because in any case, the two solutions are the same, so the ratio will be constant and fixed by what is happening during inflation. So this guy is delta sigma over sigma 0 during inflation. Okay? And what is it? So we discovered that delta rho sigma divided by rho sigma during the evolution of my oscillations is nothing else than twice h over 2 pi, which is the typical fluctuation of delta sigma, divided by 1 over sigma 0 during inflation, whatever value it is. Okay? All right. So you say, Bo, okay, why should I care about this? Well, you care because now if I compute the total curvature perturbation, so let me go, sorry, let's keep this, this one, and let me go to the other blackboard. Let's change this. So now what is a total curvature perturbation that is the one that will be transmitted to radiation when inflation ends? What is a total zeta? If you remember, the total zeta was psi plus h delta rho over rho dot. Okay? Let's compute it in the gauge in which psi equals 0. So this will be h delta rho over rho dot. That we learned it already many times. But then, what is delta rho divided by rho dot? Delta rho and rho dot are the total energy density. So, but here we have 2 degrees of freedom, this scalar field and the inflaton. So it will be h, and here I have delta rho, let's say phi, plus delta rho sigma divided by rho dot total. So I don't split it here. Okay? But now what I can do, I can multiply term by term, up and down by the corresponding rho dot. So I can write it down as h delta rho phi divided by rho dot phi times rho dot phi divided by rho dot total plus h, the same thing for the other degrees of freedom, delta rho sigma divided by rho dot sigma times rho dot sigma divided by rho dot total. Okay? But notice now that this first object here, this one, is nothing else than zeta phi. This object here is nothing else than zeta sigma. So what is I get at the end of the day? I get zeta phi which multiply by rho dot phi divided by rho dot total plus zeta sigma rho dot sigma divided by rho dot total. All right? So that's a generic formula that you can also, anytime you have more than one fluid, more than one degrees of freedom, this kind of separation is always useful to think of. And now, here it comes the key point. The key point is that, in general, the curvature perturbation will be the sum of these two pieces, but suppose that for some reason, that's the assumption, the first piece is subleading, or in any case, is smaller than the second one. Okay, it's an assumption. Suppose that this guy, I can neglect it compared to this. Of course, you have to check under which parameters this is true, but in general, you can do it. Suppose, for instance, the zeta phi, that goes like 1 over epsilon, and then you say, well, I pump up a little bit the epsilon to kill the fluctuations of the inflaton field compared to the other one. So let's suppose that, in fact, the assumption that I'm going to make from now on is, in fact, that the zeta is dominated not by the inflaton, but by the other field, by the sigma. Again, you have to check in your parameter space when this is true, but for sure you can find a parameter space which is true. So zeta is more or less zeta sigma times rho dot sigma divided by rho dot total. Okay? Zeta sigma, we computed it from there, because zeta sigma, you remember, zeta sigma is of order of 1/3 or minus 1/3 delta rho sigma divided by rho sigma. We computed, so it's of order of minus 1/3 with a 2 factor here. From there, h over 2 pi times sigma 0 during inflation. So let me put also inflation here. Okay? So you see, if h divided by the vacuum station value during inflation is of order of 10 to minus 5, then I can reproduce a fluctuation that I know. Okay? But there is a factor in front. Okay? So what I do with this factor? What I do is the following. At some point, the scalar field, sigma, this curvaton, it's called the curvaton, in fact, because you see it provides the curvature perturbation. That's the reason why it's called the curvaton. Not very fancy name, not lots of fantasy, but okay, this is what the people use it. So there is a factor in front, and the question is, what is this factor? Well, we don't know, of course, but let's suppose that at some point this curvaton field will decay, like the inflaton. Okay, it's very quite impossible to have a scalar field which does not have any interaction whatsoever. It doesn't talk to anybody. Sooner or later, this guy will decay. So when it will decay, it will transfer all its curvature perturbation to radiation, let's say, because suppose that this guy will decay into light degrees of freedom. So what I do, I compute this object here at the time of decay. Okay? And let me call this ratio, it's traditionally called, for some reason, small r, which is not the tensor to scalar ratio that I defined yesterday. It's another parameter, but let me use the same symbol that people use in the literature in the case in which you are curious and you go to some paper to look at it. It's r, in fact, let me call it, just to be sure, rdk, rd, in such a way that you don't make any confusion, but it's a parameter computed when the guy decays into radiation. So at the end, the prediction will be that I have to impose the zeta, I have to impose to be, if you remember, 1 over 5 zeta is delta t over t. So I impose that this guy is 5 times 10 to minus 5, more or less. And this has to be zeta sigma times rd. Okay, this coefficient rd. And so it's of order of rd times 2/3 h over 2 pi sigma 0 during inflation. Okay? So you have a lot of parameters here to play with. Of course, you don't know what h is, you don't know what sigma 0 is, you don't know what rd is. So you can do whatever you want. Okay? But what is the key point here? The key point is that you need this RD times h over sigma 0 to be of order of 10 to minus 5. That is something that you have to fix if you want this guy to produce the curvature perturbations. Okay, so that is what it comes out from this model. So this model is basically a very simple model in which you decouple, in fact, the prediction of the single field model of inflation. Because, for instance, if I now ask you, okay, the amplitude of zeta will be 10 to minus 5, but what will be the spectral index of the curvature perturbation in this case? Can you give me the answer after all this week? So the spectral index of zeta, so the power spectrum of this guy, if it is induced by this, will be the power spectrum induced by what? By the delta sigma, right? Because here h over 2 pi is delta sigma, so the power spectrum of the zeta will be proportional to the power spectrum of the delta sigma. And we learned that the spectral index of zeta minus 1 will be proportional, therefore, to the spectral index of sigma minus 1, which was minus 2 epsilon, right? So in this model, the spectral index is not the one that we computed yesterday. It's completely different. Well, not drastically, but it's different. Also, in this model, you see, if you want to suppress the fluctuation of the inflaton field compared to the curvaton, you see the fluctuation of the phi, if you remember, was h over 2 pi m Planck square divided by 2 epsilon. Okay. So no, in fact, the 2 it's only like this. So you see, there are two ways to suppress this number. Either you take epsilon a little bit larger, or you drop h, right? A model where h is very small will do, okay? Because if you take these numbers more than this, you can always find parameter space. If h is small enough, because sigma 0 will be also of order of h, you can do it. But remember that when I drop h, the tensor modes also drops, because the tensor modes were going like h over 2 pi divided by m Planck. So the prediction of the curvature model is that we should not see tensor modes, first of all, if you use this trick of dropping this object by dropping h. And also the spectral index should not be the one that I computed yesterday. You remember 2 eta minus 6 epsilon, but it should be this one. Okay? So that's another different prediction of this model here. But now I want to spend my rest of the time to, in fact, to give you the most drastic difference between the two models, which is non-Gaussianity. That's the reason why we are talking about all this. Okay, so let's compute in this model F and L. Okay, the simple model, massless scalar field with basically no interactions, and let's compute the F and L. And then I think I will be done. And I want to show that, in fact, this F and L is extremely large. It can be extremely large. All right, so first of all, we know that zeta is zeta sigma. Let's compute zeta sigma. We said that is equal to minus 1/3 delta rho sigma divided by rho sigma. Okay? And what we have done, well, we simply say that the rho sigma is equal to m square sigma square. Okay? So this is going to be minus 1/3. Let me repeat the computation I've done before, but this time I go not only linear, but I go quadratic. Okay? So it's going to be m square at the numerator. Then I have twice sigma 0 delta sigma, because I write down the sigma as sigma 0 plus delta sigma. And then I will have, when I take the square of it, I will have the sigma 0, which is just the background, plus twice delta sigma square. Okay, divided by m square sigma 0 square. Okay, so what I get minus 1/3. The m square goes away as before, so I have twice delta sigma over sigma 0 plus delta sigma divided by sigma 0 square. Okay. Now I write down the zeta that comes out from this model. It is zeta sigma times RD, right? It was what we show in the other blackboard. So now what is going to happen? I have zeta sigma. Well, let's write it down like this. I have RD, and then I have minus 1/3, and then I have twice delta sigma divided by sigma 0 plus delta sigma divided by sigma 0 square. And now what I do, I identify the linear piece. The linear piece is this one. So I write it down as RD divided by 3 times 2, delta sigma divided by sigma 0, plus, well, let me repeat the thing because then I will clear why I'm doing it, RD divided by 3, and then I have delta sigma divided by sigma 0 square. This is the linear piece. So this I identify with my zeta Gaussian, because delta sigma is Gaussian. All right? And now, so zeta sigma, zeta Gaussian is 2 over 2 RD divided by 3, delta sigma over sigma 0. So from here I get that delta sigma over sigma 0 is nothing else than 3 over 2, 1 over RD, zeta Gaussian. Okay? So now I use this information to plug it in the second term. I will have plus RD divided by 3, and then I take the square of it. I will have 9 over 4, then I will have 1 over RD square, and then I will have zeta Gaussian square. Okay? Right, so now, sorry, it's a little bit of a mess. I go here. It will be zeta Gaussian plus, I have a 3 here, 3 over 4, 3 over 4, and then I have 1 over RD times zeta Gaussian square. So that's the final result. If I didn't screw up the algebra. So now we are back to the definition of the non-Gaussianity. Remember that I define the FNL to be zeta equal to zeta Gaussian plus FNL, zeta Gaussian square. Well, sometimes people put a 3 over a 5 here just because, remember, for matter was the relation between phi and zeta was 5 over 3. But let me use this definition. That's not very important. The important thing is that in this case, if I compute the FNL here, I will have this number here, 3 over 4, 1 over RD. Okay? And now you see the result. The result is, it depends on this amount, what was RD. Remember, RD was R dot sigma divided by R dot total at the time of decay. Okay? Now, this is more or less what it is. Suppose that the universe was radiation dominated when the inflation when this curve atom decays. So this guy is minus 3h rho sigma divided by minus 4h rho radiation. So it's going to be more or less 3/5 rho sigma divided by rho radiation. Okay? So you see, if the Courbaton decays when its energy density is smaller than the radiation, suppose that this ratio is smaller than 1 or much smaller than 1, so it does not dominate the energy density when it decays, this FNL can be much larger than 1. Okay? Which is a little bit surprising because if you think about it, this scalar field is not even interacting. It's not nonlinear. But then nevertheless, it inherits you can see, in fact, in another more complicated way, that it inherits the nonlinearities from gravity, and therefore it decays when the non-Gaussianity is very large. So one of the predictions of this model is, in fact, the simple construction is, in fact, that the perturbations are given by the Courbaton field. The spectral index is different from the single field models, but above all, this number can be in principle much larger than unity. So you understand that if one day we are lucky enough to measure these non-Gaussianity parameters, and it turns out to be, I don't know, 10, 100 or something, well, the limits are already below 100, but in any case 10, let's say. As I said before, all single models of inflation will be ruled out. So considering only 1 degree of freedom will be not enough, and one has to resort to a construction which is slightly different, for instance, the one that I presented today. It's one example. There are many other examples where you add extra degrees of freedom in your model, and you're going to construct some FNL which is different from 10 to minus 2 that you have in single field. Okay? So that's an information you should also take home, the fact that there are many observables from inflation that are interesting. Of course, the amplitude of the power spectrum, the spectral index, as we have seen, is connected to the temperature anisotropy. The tensor to scalar ratio, which is the amount of tensor modes, but also the nonlinearity during inflation, which is governed by this parameter FNL. And the people are looking for it in a really precise way. So let me also use the last 10 minutes. Sorry, we don't have a break today, so stay with me. The last 10 minutes, I want to show you, I want to tell you, in fact, how people are after this parameter, okay? People have tried in the CMB with Planck. The bounds are more or less coming from FNL smaller than about, in absolute value, 10 or so. I don't remember the exact number, but it's about 10, which again, as I told you many times already, it's not a failure of perturbation theory because the real parameter of expansion is this. So we are measuring the CMB, the nonlinearities of the CMB anisotropy up to a factor 10 to minus 4, because 10 is the limit, this is 10 to minus 5, so you get 10 to minus 4. So you can imagine that these CMB anisotropy measurements are so precise that we are able to say that the CMB is linear up to 1 part over 10,000. Okay, so it's quite pretty nice result. So how people are thinking to improve these measurements using the last case structure. Okay, so there is an experiment which is called Euclid, which is taking data right now, which one of the goals, not the main goal, but one of the fundamental goals of these experiments is to either detect this FNL, that will be great, or to give bounds which are even stronger than this. So what is the underlying idea? The idea is the following. Let me sketch it, because this is something that might hurt in the future, not very far future, luckily, which is the following. They want to measure this non-Gaussianity in the bias. Okay, what does it mean? So what happens during evolution of the universe is the following. You build up these fluctuations during inflation. As I told you many times, they re-enter the Hubble radius, and then they start collapsing because gravity is attractive. Okay? So when you think in terms of linear perturbation theory, a Gaussian, suppose that you have you go to your laptop and you say to your program, Python or whatever, you say, I have take values of a given observable from a Gaussian distribution and construct, let's suppose, a two-dimensional in space pattern of these fluctuations. So what you're going to have your box, okay? And then you have ISO curves, basically, where you have peaks. So you're going to have peaks of these fluctuations in some regions. So you get peaks. If you think in terms of one dimension, what is going to happen is that if you plot, for instance, delta rho over rho as a function of space, let's say, you are going to have some distribution like this. Okay, you have peaks. In fact, it's a beautiful chapter of statistical theory to take a Gaussian and to characterize the statistics of the peaks. What are the peaks? Are the points where the gradients of delta rho over rho is 0 because it's an extremum, but also you have the Laplacian of delta rho over rho is smaller than 0 because it's a maximum. Okay, so you construct in 3 dimensions these peaks. Usually these peaks are spherical, so if you think in terms of 3 dimensions, they are sphericals. There is a spherical symmetry. In general, the peaks are not exactly spherical, depends on the amplitude of the peak, but you think in general they are ellipsoid. But when the peaks are very large, they tend to be spherical. All right, so now suppose that you have created this realization. The perturbation re-enter the horizon, they have this distribution in space, and the question is where you are going to form more likely halos of cold dark matter, for instance, where? Around the peaks, obviously, because they have the largest amplitude, okay? And what happens inside the halo? Well, the galaxies will form inside halos, okay? So if you ask yourself, what is the two-point correlator? What is the statistical distribution of galaxies? Well, you take your distribution initially, and then you look at the peaks, and then you identify the peaks with, so every time you see a peak, you identify, you label it a halo, and therefore a galaxy, roughly speaking. So what happens is that when you compute the two-point correlator of the peaks, so let me call this quantity psi. So psi, as a function of r, is a two-point correlator of the peaks. Let me put here pk. This two-point correlator is not the two-point correlator of the underlying field, of the underlying delta rho over rho, but there is also a kind of enhancement factor, which is called, people call B squared, the bias factor. So this is the bias, which turns out to be of order of sigma, so delta, let's say delta rho divided by rho 0 at the peak. So the value here, so this is the value, for instance, of delta rho over rho 0 at the peak. Okay, the amplitude, if you like, divided by sigma square, where sigma is the variance. Sigma is the two-point correlator of delta rho over rho, the variance, in fact. Okay? So this is what happens. It happens, the information, the most important information is that if you have an underlying Gaussian field whose two-point correlator is this, the two-point correlator of the peaks is not the two-point correlator of the underlying thing, but you get an enhancement factor. That is the reason why the galaxies have a distribution statistically, which is not the distribution of the cold dark matter, by which they are basically, the cold dark matter is able to form these gravitational wells under which the baryons and so on form, but it's biased, so there is a bias factor. They are much larger. Okay? So why I'm saying that? Because now, if you look at the the delta rho over rho. What is delta rho over rho? If you use Poisson, the Poisson equation, delta rho is in fact proportional to the Laplacian of your gravitational potential, right? This Poisson equation. Now, the gravitational potential is in fact, as we have seen, related to the curvature perturbation with some coefficient. So delta rho is proportional, or delta rho over rho if you like, is proportional to the Laplacian of zeta. Okay? But now suppose that zeta has some non-Gaussianity in it. So what we have to do, you have to take the Laplacian of what? Of your zeta Gaussian plus FNL zeta Gaussian square. Okay, well, let's do it. This is going to be the Laplacian of zeta Gaussian. Then here you have two kinds of terms. You have zeta Gaussian times, well, FNL, let's say, FNL, zeta Gaussian times the Laplacian of zeta Gaussian, plus you have terms that goes like zeta Gaussian, the gradient square, but I can neglect them because I am at the peak. So I can neglect this, okay? So I only keep, sorry, and also this is proportional to FNL. I can only keep the second term. Of course, when you do numerical simulation, you keep everything, but let me do this simple approximation. So what is delta rho over rho in this case? It's going to be proportional to the Laplacian of zeta of the Gaussian component plus zeta Gaussian plus FNL, zeta Gaussian, the Laplacian of zeta Gaussian. But this is, I can write it down as delta rho over rho Gaussian plus FNL zeta Gaussian times the delta rho over rho Gaussian. Okay? Now think to go in momentum space, because in momentum space what happens is that since delta rho over rho is proportional to Laplacian of zeta Gaussian, let's say the zeta, the Gaussian component, in momentum space I know that delta rho over rho Gaussian goes like k square times zeta Gaussian. So now I can replace this object here, I can replace it by FNL, this guy square, divide by k square in momentum space. I'm not technically speaking very correct, but let me give you the argument. So when I have non-Gaussianity, the delta rho over rho gets a contribution that is that goes from FNL, goes like 1 over k square. Okay? So when I now measure the galaxy correlation function, or the peak correlation function, because I identify peaks with galaxies, if you like, in a very rough way, the bias coefficient will receive a contribution from this piece here. And when I go to very large distances, so I have my Euclid experiment is detecting galaxies, measuring the 2-point correlators, and I need to go to very large distances because I need to squeeze this k to 0. But going to large distances, and it means that I have to go back in time at larger and larger redshifts. So of course I have a statistics which is dropping down, so it's not an easy measurement. But they are trying now to detect this increase as 1 over k square in the data, this piece here. Okay? So it's a very well-defined behavior, and they're after this behavior. So they want to see the increase of the bias factor as a function of 1 over k square, which is due to, in this case, to the presence of non-Gaussianity. Okay? And they claim that they can deal with the data in such a way to drop this FNL, the bound. They claim that they are able to detect up to FNL over the unity. Okay, so now the experiment is working, and we are now eager to see if they will be able to measure even FNL over unity, or to give a bound. Of course, the most exciting part of the sentence will be if they measure it, because if they measure it, that will be a fantastic result from the point of view of cosmology, because not only you test for the first time the nonlinearities of coming from inflation, but also, as I said before many times already, you ruled out all the models of inflation that are driven by a single scalar field. I mean, meaning that the perturbations are due to a single scalar field. Okay, so that is something that you should have your eyes on in the next future. Next future means a matter of 1 year or so. The time to analyze the data, or a little bit more, of course, but in any case, not 10 years. Okay, so with that, I think I will leave you, and I thank you for your enthusiasm and your attention, because you have been very all the time very with me. So I know it's not easy, and I will put on the Indico page the set of notes that I have in PDF, which in fact they are already on the archive, but I put the updated version, and you can have a look. If you have more questions, you can write to me, and we'll see. All right? So thanks a lot.